So I was wondering, Kris, what do you think would be your advice for young chemists, maybe at the student level, uh, why they should approach a continuation of their career in polymer science, polymer chemistry, polymer-related subjects?
This is a very complex question because on one side, maybe 50% of all chemists work with polymers, and very often they have no idea how to control this polymerization, what these polymers are. So in that case, they will have it as a basic fundamental education which would make their life more successful in industry. But from another perspective, you may say that the most interesting things happen in the interfaces. So it's not only just a polymer-polymer, but maybe polymer biomolecule, maybe polymer and surface, or maybe polymer and the energy-related system like batteries, or maybe environment for membranes, for other things. So for that, it would be important that these students, they would be also broadly educated. They need to understand the other areas which would be related to these fields, which they are not necessarily specialized. So this is probably breadth is very important, but also depth, that whatever they do with these polymers, they may be, should be better than anybody else. But for real success, I think they should be just passionate what they do. And passionate means that instead of sitting on a couch and watching TV, they should be really dreaming about chemistry.
So Kris, how do you see regarding future breakthrough and future fundamental advances regarding sustainability aspects of polymer science, polymer chemistry, this case?
Yeah, I think that sustainability is probably not only related to polymer chemistry, but to chemistry overall, which means how we can have a greener chemistry with lower impact. And I think for particular case of polymers, it would be related to controlled degradation, potentially controlled recycling processes. And one of these possible recycling, what I discussed 2 days ago, is by depolymerization back to monomers. This is probably the cleanest way to make the same materials of high properties without really any deterioration based on the recycling process. And the other aspect would be how we can make these polymers in a cleaner way. Can we make them without toxic organic solvents? Can we do it in water? Can we do that in sometimes presence of air without any expensive equipment? Can we do it at lower temperatures using catalysts and making them more selective? But another approach would be to think about really renewable resources. So can we switch from oil-based chemistry to something which would be really based on plants? And this is a challenge because you need to make monomers in a clean way, and typically monomers should have one functional group in order to have a linear polymers, but very often you have many of them, and in that case you will get a cosmic material which may be good by itself. So I think this is a very broad question of sustainability, but I think this is something which we must address in 21st century.
Kris, you have been involved in several grand challenges that characterize polymer chemistry in the last 50 years. First of all, was probably one of them was gaining control over polymerization processes, then turning these processes into more sustainable. What is the next grand challenge in your vision?
I think that many things changed during the last 50 years, and you're right that in some sense one can start with a very fundamental mechanistic status before understanding how things work. it's difficult to make any materials. So the first aspect would be really to learn how you can make it cleaner, how you can make it more selectively, how you can really go from 90% yield to 99.9999% yield. So this would be really selectivity similar to biological systems in some aspects. But I think that really next thing is really why to make it. Why to make certain materials, what is the target material properties. And this would be practically related to most important issues in life sciences, which means biomedicine, with energy and environment, with sometimes any kind of the advanced material. So can we do that again for purpose in some sense? And of course, sometimes it's very difficult to predict what kind of properties you may have. Either you can make 1,000 experiments, sometimes for high throughput techniques, or you potentially can have a, like a eureka moment, and then you think this would be one which would be the best. Sometimes it works, sometimes it doesn't. So can we help maybe with some modeling or computational predictions? It is very difficult for polymeric materials because they are very viscous and rarely you can reach thermodynamic equilibrium. So sometimes you have a kinetically trapped system, and it's a question, can computation really mimic that? And can you really go to more complex and faster computational techniques and predict what kinds of properties you may get? Sometimes it works, sometimes it doesn't. So very often you still need to have a sufficient number of experiments to build these, even to feed to machine learning with a large data set. So I still believe that probably all of these challenges which face our society in the life sciences, in environment, with energy, can be somehow solved with chemistry, and especially macromolecular chemistry, which is really providing so many fine solutions. So in some sense, we want to make molecules with every part of this molecule designed and precisely controlled, like in biological systems. And in that case, they can sometimes behave in a way that they can contract or expand like our muscles. They can provide information, they can self-heal, or maybe in the future they can self-reproduce.
Thank you.